In this new section, we are going to talk about lines and planes. Okay, we're going to talk about lines and planes. Well, we all know that 2 points determine a line in R2. In R2, 2 points, of course, determine a line. If you have the point P1, which is x1, y1, and the point P2, which is x2, y2, certainly there's only one line that connects them. And of course, the line goes on forever. Okay. Now, every line can be written in the form ax plus by plus 1c is equal to 0. Every line can be written that way. And this line, if it's going to contain these 2 points, this line must satisfy their equation ax1 plus by1 plus c equals 0 and ax2 plus by2 plus c is equal to 0. Just writing it slightly different. I'm going to write it as a system of equations. Again, there are ones here where the variables are just a, b, and c. That is, the first equation is x times the variable a plus y times the variable b plus 1 times c equals 0. And the second equation will be x1a plus y1b plus 1c is 0. And x2a plus y2b plus 1c equals 0. And this transfers into this system of equations. A homogeneous system. Well, I take that back. This is our system of equations. It's a homogeneous system of equations because all their equations equal 0. Now, please remember, if you have 3x or 3a plus 4y plus 7z minus the number 2 equals 0. If you have the other equations in this form, this is not homogeneous. You need to bring the constants over to the right side. And in the case above us, that is the case. So it's a homogeneous system, and we can write down the coefficient matrix x, y, 1, 0. Second equation is x1, y1, 1, 0. And then x2 and y2 and 1c, or just 1, and 0. Okay. Now, we want this system to have non-trivial solutions. Why is that the case? Well, do you think that this equation, namely the last two, do you really think, I'm sorry, I mean the top one, do you really think this line has an exact answer for x and y? I mean, look, it has this x comma y point. It has this x comma y point. It has infinitely many solutions. The only way that system that I'm erasing now, or if you want to look at the right-hand side with the matrices, the only way it's going to have a non-trivial solution is if, since it's homogeneous. A homogeneous system of equations has a non-trivial solution if and only if that coefficient matrix has a 0 determinant. We want this determinant x1, y1, 1, or x2, y2, 1. We want this to be 0. In fact, this is the equation of the line. This here is the equation of the line. That's the equation of a line. Believe it or not, that's the equation of a line. And calculate the determinant and set it equal to 0. That's the equation of the line that contains the 2 points, x1, y1, and x2, y2. Okay. So let's do a real life example. Suppose you had the points 2, 5, and 3, 7. And I notice if I double the x and I add 1, if I double 2 and I add 1, I get 5. And if I double x and I add 1, I get 7. So you double x and you add 1 and you get the y value. Okay, so this is kind of secret. We won't tell anyone that. That is, I'm just going to use the 2 points and this formula at the very bottom, and I'm going to get the equation of their line. First I write x, y, 1, and then I write x1, y1, 1. Well, maybe that's x1 and that's y1. That's 2, 5, 1, and x2, y2, 3, 7, 1. Now, we don't have to worry about taking the absolute value because there's no reason why I couldn't interchange those points. That is, interchange these 2 rows. And then the the determinant will have a sign change. But we don't have to worry because it's 0 anyways. Okay. So I'm going to put the 0 in front of this. Again, this is the equation. Just calculate this determinant and set it equal to 0. Now, what I'm going to do is to get a lot of zeros in the third column is to just do row 1 minus row 2 and to do row 3 minus row 1, minus row 3. So this determinant is going to become, the first row didn't change, but now I'm going to do row 1 minus row 3. X minus 2, y minus 5, 1 minus 1 is 0. And now I do row 1 minus row 3. Row 1 minus row 3. I get x minus 3, and y minus 7, and 1 minus 1 is 0. It's a friendly determinant. We're going to expand about column 3, and I hate 1s. When I expand about columns 3, when I cross off row 3, there's a 0 there. Don't bother. When I have to cross off row by row, when I cross off this row, there's a 1 there. Don't bother. Only when I cross off that row, I get a non-zero number. So I get negative 1 raised 2. That position is the first row, the third column. That number is a 1, and the determinant that survived is that determinant. I don't know why I put 2 bars already. The determinant is x minus 2, y minus 5, x minus 3, y minus 7. If you think this is too long, not a problem at all. Do the spaghetti roll here. Okay. Now this is an even number, so negative 1 to the 4 is even. Times it is 1. Times it by 1, it's still 1. So the answer is it's just this determinant. It's x minus 2. Okay, times y minus 7 minus x minus 3 times our y minus 5. Okay, let her see what I get. And again, it equals 0. So that's the equation of the line. And what's puzzling me is I'm seeing an xy portion in there. Okay, let her see what happens when we FOIL this out. We have problems, have to redo it. So when I FOIL this out, I get xy. Oh, actually, this shouldn't be a problem. Minus 7x minus 2y. So 0 is equal to what I'm writing. Plus 14. Plus 14. And I take away this. I take away x times y. I take away 5x. I take away 3y. And I take away 15. That is, I add 15. Okay. The first thing I'll say is xy minus xy cancels. I saw that, but then I saw other combinations I didn't like. And for some reason, I thought they were xy combinations. We have negative 7x minus negative 3y. That is negative 4y. Oops, not having a good day. Negative 7x minus negative 5x's. That's our negative 2x's. So I dealt with those two. And negative 2y minus a negative 3y is plus y. And 14 minus 15 is negative 1. So 0 is equal to negative 2x plus y minus 1. If I bring these two to the other side, the negative 2x becomes plus 2x. The negative 1 becomes plus 1, and the y stays. But that is what I said the equation was supposed to be. Now, if you wanted to, you could have done the tic-tac-toe. Let's see and learn right here on the spot if that's going to be easier than subtracting two sets of two rows. Row 2 minus row 1 and row 3 minus row 1. Now, the tic-tac-toe would have been, just remember that the determinant equals 0. So, well, let me not write that just yet. So you write down the determinant x, y, 1, 2, 5, 1, 3, 7, 1, and then you repeat the first column, and then next, the second column. And here you get 5x plus 3y plus 14, and then you take away 15 and 7x and 2y. 5x minus 7x is negative 2x, and 3y minus 2y is plus y, and 14 minus 15 is negative 1. And this equals 0. But that just means that 2x plus 1 is y. Or if you prefer, y equals 2x plus 1. I only wrote the y last because I'm bringing everything except y. I'm keeping y on the right side, and there it is. I brought everything to the left side. So whatever you prefer, do it that way. Just write down xy1, write down the first xy point on the line and then a 1, and then write down on the third row another xy point and then the number 1. You always have to write the number 1 in that last column. I'll show you what I mean by doing one more example. Suppose you come to know that the points 3, -2 and 4, -5. These are on a line. And I randomly made them up. I don't know if it's easy to figure out or not. But if you want the equation of this line, all you do is you write down xy, and then the first point, and then the second point. And this is what you need to study. If you want to find the equation using determinants, if you want to find the equation of a line that contains two given points, first you write down xy, then you write down the first point, then you write down the second point, x first and then y, and then you put ones. And whatever you get, it has to equal 0. Whatever you get, it equals 0. It equals 0. You want to use the spaghetti method? Fine. It's xy1, 3, -2, 1, 4, -5, 1. Repeat the first column. Repeat the second column. Tic-tac-toe. Or spaghetti, excuse me. So we get that 0 is equal to -2x plus 4y minus 15 minus, now we go the other way. That product is -8, that product is -5x, and that product is plus 3y. You have to know how to multiply. It's not negotiable. -2x minus -5x is 3x. You have to know how to add. 4y minus 3y is 1y. -15 minus a -8 is a -7. You want to set it equal, get it to, in the form y equals -3x plus 7. Okay, so you don't have to use the point slope formula anymore. It's just write down xy, write down one of the 2 points, write down the second point, put ones down, calculate that determinant, and say it equals 0. So, when you quote calculate the determinant, clean it up. Get it to be 3x plus y minus 7, and that equals 0. You want to solve it for x? Well, then do something called algebra. The bottom line is the linear algebra is done. It's just a determinant. So that's a nice way to find the equation of a line using determinants. We want that determinant. We want that system of equation to have an infinite number of solutions. We want it to have a non-trivial solution. We want it to have a non-trivial solution. Now, I'm interested in what's going to happen if, say, their line is x equals 5. That is, suppose you have the point 5, 3 and the point 5, 7. When I look at these, I say, you know what, no matter what y is, x is 5. That's the equation of the line. Let's see what happens. You have xy, and then the first point, and then the second point, and then, of course, ones. Now, you know what? Here, it's just in me. I need to reduce this. I'm going to do row 3 minus row 2, because 5 minus 5 is 0, and 1 minus 1 is 0. The first row did not change. The second row did not change. 5 minus 5 is 0. 7 minus 3 is 4. 1 minus 1 is 0. I will expand about this third row. That means I have to cross off column by column. But crossing off this column doesn't contribute anything because I'm going to multiply by 0 at some point. Same thing here, it is a 0. Only that number comes into play. It's -1 to that position. Third row, second column. Times that number, which is the 4. Times the determinant that remains. The only thing that remains is x5 and 1, 1. Okay, that's an odd number. -1 to the 5 is -1 times 4 is -4 times this determinant, which is x minus 5. So I get -4x plus 20. This is equal to 0. And that's the equation of the line. You may say, but wait a minute. You didn't get x equals 5. Well, divide by 4. Bring this to the other side, and you get 4x is equal to 20. So x is 5. And you really should get this far. You shouldn't say, oh, that the equation of the line is this. That is the equation of the line, but it's not in simplest form. Okay, so x equals 5. So it works. I was thinking the determinant would give me something unusual, but the theory says it shouldn't have. Somehow I thought it would be indeterminate, but rethinking that, indeterminate is like when you divide by 0, and we're not dividing by anything. Just evaluating a determinant. There's no division involved. Okay, and I'm sure that if you wanted y to be 5, it would work out the same way. Okay, now we want to talk about a line in R3. How is a line, and what do we know about a line in R3? In R2, you can use a point and a slope. In R3, it's a little bit different. You need a point and a vector in the direction of the line. Suppose you have this point. We'll call it P1. X1, Y1, Z1. Actually, let me just make it a little bit lower. So, you have this point P1. Okay? And you have a vector U. And the vector U is equal to the point ABC. Now, you want a vector, you want a line. Well, let's first get a vector. You want a line that crosses P1 and is parallel to vector U. That is, you want that line. You want that line. Okay, and in red, I'll put vector U. So all I did was I went to P1, and to the best of my ability, and I think I made it a little bit too short, but I drew vector U. I went to P1 and I drew vector U. That is, this angle with the x-axis, and here's a horizontal, and that angle are the same, and those two vectors should be the same length. Since they don't look it to me, I'll just make it longer. Okay, so that's the vector. And that's the vector U. And now we want to find the equation of the line, not just the red part, but the whole entire line. The whole entire line. So what we can do is, let's draw another picture. Here is vector, well, no, let me not draw vector U in this picture. But what I am going to do is P1 is x1, y1, z1. And I'm going to draw a vector that goes right there. I'm going to draw a vector w that goes right there. So on the side up here, I'm going to say that w is a vector that goes to points. The head of the point is x1, y1, z1, and the tail is the origin. Okay? Now that I'm there, I want to add on not exactly vector u, but maybe 2 times u, or maybe 0.5 times u, or maybe 17 times u, or maybe -1 times u, or -1.5 times u. That is, so since I'm not writing that much, let me just put w here. W is the point P1. All right, the equation of the line, we'll call it L, is, first, you start at the origin and you add w, which is a concrete vector. We know the length. The length of w is whatever it is. But now, I'm not going to add u, but I'm going to add any multiple of u. Now, this vector, we don't know. T times u, it depends on what t is. Okay, and we should say that t is can be any value between -infinity and infinity. So, but basically, if this is the line, if that's the line you want, you go from the origin and you add a vector that goes to any point on that line. And then you add a multiple, and then you find a vector in that direction. Any vector in that direction. And then you add any multiple of it to the vector w. You add any multiple of that vector. That vector is u. We're adding any multiple of u. So this is the equation of the line where w is a point. W corresponds to a point on that line, or it's the vector that goes from the origin to a point on the line, and u is the direction. So we just needed a point and a direction. In the first graph, I had my directional vector, and I had a point. And in the end, just using those 2 pieces of information, I found the equation of the line. Okay. So if you call a corner of your room that you're in right now the origin, and you hold up your pen or your pencil, and you imagine that it's a line, that is, it continues in both directions, you now know how to find the equation of that line. If you know the vector that goes in the same direction, and you know a point on the line, a point on that pencil, you're in business. So, suppose you have the point 7, 4, -8, and you want a line that contains, just so I don't have to write it again, it contains point P and goes in the direction of the vector u, which is negative 3, 4, 5. You want the equation of a line. You want the equation of a line. You want the equation of a line that contains a point P above and goes in the direction of U. All right. And generally we call that vector x. I mean, we call the line x. Maybe you put double arrow on top. In any case, we know that it's w plus t times u. Vector w plus tu. Well, vector w, I'm just going to call it the vector whose head is here, plus any multiple of u, negative 3, 4, 5. You really should state something about t. T is between negative infinity and positive infinity. If you want some point, so here it is. This is the equation of the line. This is the equation of the line. Okay. This is bold x. Now, if you want some points on this line, well, let t be 0. So 7 plus 0 times negative 3 is 0. 4 plus 0 times 4 is 0. Sorry, it's 4, of course. And negative 8 plus 0 5s is negative 8. This is where, that's the point that was obtained by letting, on the line, by letting t equal 0. Well, now, if we let t equal 1, well, you're going to have 7 plus 1 times negative 3. That is 7 minus 3, which is 4. And then you're going to have 4 plus negative 1 times 4, which is 0, trust me. And negative 8 plus 1 times 5 is negative 3. That's the second point on the line. If you let t equal 2, or t equals 1.8312, you'll get another value, another point. You'll get 1 and 12 and 2. So there are many points on that line, and they all come about by you picking different values of t. Now, if you notice, each point has an x value, a y value, and a z value. Some or all of them might be 0. None of them might be 0. X, y, and z. X, y, and z. Okay. So let's look at what we have in general, and then we can learn another way of writing down the equation of a line. Okay, but I think I didn't I don't think I had what I wanted. Okay, now I do. Okay. Wanted to keep their equation of that last line. Now, we know that x is equal to vector w plus t times vector u. And this is all in R3. And if we call the first point, the first vector, I don't know, x1, y1, z1, plus t times, and we'll call u a, b, c. So basically, we have x1, y1, z1 plus t is like a scalar, so we have ta, tb, tc, and adding, we have x1 plus ta, and we have y1 plus tb, and lastly, z1 plus tc. Well, this is what x is, and that's what y is, and that's the z value of the point. Remember, please, and let me write it a little bit differently. This x is not this big X in front. Alright, so what I'm about to write is what's called the parametric equation of the line. Or actually, sorry, the parametric equation of a line is x is x1 plus ta, y is y1 plus tb, and z is y1, sorry, z1, I'll change that, plus tc. This here is the parametric equation of the line, of the same line. A moment ago, we had that x was 7, 4, negative 8, plus t times negative 3, 4, 5. So x will be, so you can write it down as follows. You can do it this way. The order you write it is up to you. You can first write x, and then y, and then z, and then you write those numbers. X is 7, y is 4, z is negative 8. And then you write negative 3 plus 4 plus 5. And those last ones get a t. Remember, that's x1. Well, that's what I put. And then y1. Oh, y1 is 4. That's what I put. And then z1 is last, which is negative 8. That's what I put. And then I always put, well, I put the t's at the end here, but then I always added t times the number. I always added t times the number. And those numbers were from the vector. Negative 3t I added, plus 4t, plus 5t. So you can go from you can go from this, we can go from this form, which is the same as this form, to parametric. Okay. But now there's another form. I'm going to keep the parametric in front of us, and now we're going and erase the rest, at least on the bottom. Now we're going to look at another form. By the way, this form that I left is called parametric. First of all, let me write it down again because I wrote on it a lot. But it's called parametric because of this t. X, y, and z are in terms of t. We have that x is equal to x1 plus ta, and y is equal to y1 plus tb, and z is z1 plus our tc. And this is in parametric form. Now, if I take each of these equations and I solve for t, then all those things that equal t are equal to one another. This first equation, if I bring the x1 over, it says that t times a is x minus x1. Remember that x minus x1 equals TA. Now I divide by a. So that's what t equals. In the second equation, I bring the y1 over. So I get y minus y1 is tb. I divide by b. Do the same over here. Z minus z1 over c is equal to t. But everything that equals t is equal to itself. That is, these three are equal to one another. X minus x1 equals, x minus x1 over a, that equals to y minus y1 over b, which in turn equals z minus z1 over c. This is yet another way of saying the line, of writing the line. This is called the symmetric equation for the line. What line? Oops, for the line. L-I-N-E. What line? The line that has the point x1, y1, and z1, and is parallel or in the same direction as the vector A, B, C. So, a lot of theory there. Different ways of writing the equation of the same exact line. Let us do some examples. Suppose you want to find the parametric equation of a line through the given point and parallel to the given vector. Find the parametric and symmetric equation of the line through the given point. The line through the point P1, which is a 3, 1, 5, and parallel to the vector u, and we'll let u equal 2, 1, negative 4. Okay. So remember, the line L, we'll call it L. The line L is W, can be written as vector W plus the scalar T times the vector U. And the vector W is not the point 315, but the vector 315. What's the difference? Well, maybe that's the point. Let's just go in 2 dimensions. That's the point 31. It's just a point. But that is the vector 31. So they're not exactly the same, but unfortunately they're written the same. Sorry about that. Plus, but it is not my fault. 2, 1, negative 4. This here is the equation of line L. But we were asked to write this in parametric and symmetric form. Well, in parametric, x is 3 plus 2t. And the y value is 1 plus 1t. 1 plus 1t. The third value is 5 plus negative 4t. That is 5 minus negative 4t. That is the parametric. Now, if I solve for t in the first equation, that is, I bring this 3 over, so x minus 3 is now 2t, I'll divide by 2. So that's what t equals. In the second equation, I bring the 1 over as negative 1, and then I divide by my 1t. Same game with z. Z equals. Bring the 5 over as negative 5, and then divide by the negative 4. And that is symmetric. Now, how can you go to symmetric, say, right away? It's x minus that number divided by, that number came from the point, and then you divide by the x value of the vector. And that equals y minus the y value of the point divided by the y value of the vector. And that equals to z minus the z value of the point divided by the z value of the vector. If you can just state it that way, stop doing a million problems. Say that if you're given a point and you're given the vector that is parallel to the line you want, and you want their symmetric equations, you just do x minus the x value of the point divided by the x value of the vector equals y minus the y value of the point divided by the y value of the vector equals to z minus the z value of the point divided by the z value of the vector. It's trivial at that point because, you know, are the numbers going to be hard? I mean, are you ever not going to know how to write x minus whatever number is there? The worst it can be is just look bad. Log of 7 raised to the pi. Maybe that first number was log 7 raised to the pi. So let it be that. It's going to be x minus it. And you're going to divide by the first value or the x value of the point, of the vector. And maybe it's not very nice. Maybe it's not nice, but it is what it is. I mean, it's e to the pi to the square root of 2. It is what it is. Just put it down. So you just have to know what you're looking for. Finding the x, y, and z value of the point is simple. Finding the x, y, z value as an I, j, k component of the vector is pretty simple. It's the first, second, and third part of the vector. Okay. Now, suppose you were given the following. Now, remember, let's talk, while I erase the board, let's talk about our two-dimensional cases. When you had a line, when you had 2 points, and you wanted to use the point slope formula. If you're given 2 points, the first thing you did was find the slope. Okay? So you found the slope. And then you used the point slope formula, which means you needed a point and a slope. Well, you just calculated the slope, so you have that, and you have 2 points. And the question is, which point do you use? And the answer is it didn't matter. If you had 2, 3, and 5, 9. If you calculated the slope From 3 to 9, y went up 6. From 2 to 5, it went up 3. So the slope is 2. And then you picked a point, and you said y minus that y value is equal to 2 times x minus that x value. Personally, I don't do it this way. I don't use the point slope, but here I will. Add 3 to both sides, and there's the equation of the line. And that's when we use the 2, 3. Well, the slope is still 2. Now, what if I use the second point? You'll have y minus the y value, which is 9. It equals the slope times x minus the x value, which is 5. So y minus 9 is 2x minus 10. And if you add 9 to both sides, you get 2x minus 1. You get the same answer. Well, we're going to have a similar thing in R3. What if I give you 2 points? What if I just give you 2 points? Okay? I give you 2 points in space, and I say, okay, find the equation of that line. And all you have is the 2 points in space. Well, remember, to get the equation of a line in 3 dimensions, you need a point, and you also need a vector that's parallel to the points. Now, suppose these are the 2 points. Well, I know a vector that's parallel to this line. I know a vector that is parallel to that line. And you know what vector it is? Call this P and call this Q. It is the vector from P to Q, or Q to P. Doesn't matter. So there's a vector, and it's clearly parallel to the line that you want. You want the line that crosses those 2 points, and even in 3-dimensional space, if you have 2 points, there's only one line that crosses those 2 points. So now that you have, you calculate this vector PQ. You do head minus tail, you get the vector. And now, so now you have a vector. In other words, P is x1, y1, z1, and Q is, say, x sub 2, y sub 2, z sub 2. So PQ is a vector, and that's what we're going to call vector U. And it's the head minus the tail. Z2 minus Z1. That's the vector. But now you need a point. Well, I can use any point on the line. I can use that point or that point. I can use other points. I can use that point if I knew what it was, but I don't know what it is. So you can use any point. You can use and call it a vector. You can use that vector, or you can use this vector. Because basically what's going on is the following. Well, let me draw it down here. You have the 2 points, and that's the line. Okay? Now, you can get the equation of the line in one of 2 ways. You could start at the origin and add on that vector, and then add on t times u. You can add on any multiple of u. Okay. Or it can go like this. Here's point P, and here's point Q, and there's the line. You can first go out to point Q, and then from point Q, add on vector U. Either way, you get the same line. Either way, you get the same line. Okay. So if you're given 2 points and you want in three-dimensional space, that is in R3, and you want the equation, it's not a big deal. It's just like before. Instead of using the 2 points to get a slope and then picking one of the 2 points to use some formula, the point slope formula, instead now you use the 2 points to find the vector U, and then you use one of those 2 points, either one, to find the equation of the line. Okay. So suppose you have a line, suppose you have these 2 points. Point P sub 0, which is 315, and you also have point P1, which is 724. And you want to find the equation of this line. So first you have to find P0, P1, which I'll call U. Do 7 minus 3 is 4. 2 minus 1 is 1. 4 minus 5 is negative 1. So now I know that, for example, if this is U, then my line that I'm looking for will either be one of these gazillion lines. It'll either be this line, and please, I'm drawing it forever. It doesn't look like it, but I'm drawing it forever. Or it's this line, or it's this line, or it's that one, or that one. Notice, to the best of my ability, they're all parallel. Now, if I know that it contains that point, well then I have it. I got it. Yes, I got it. It must be this line. If it contained not that red point, but this red point, well then I still have it. It's going to be the same line that I just drew in blue, which is now drawn in green. It'll be that line. Okay. So I have the vector U, and I pick any one of the 2 points. Convince yourself that, after you pick one of them and you find the equation of the line, make sure when you pick the other one, you're like, yeah, I'm getting the same equation. Probably won't look the same, but it'll be the same. W will be, say, 315. So the line is W plus T times U, 4, 1, negative 1. This is their equation of the line. You want to write it in, remember, this is big X. What is big X? I can tell you. It's 3 plus 4t, comma, 1 plus 1t, comma, 5 plus negative 1t, or 5 minus 1t. Okay, well, that really helps, because in parametric, I just underlined the 3 answers. In parametric, you have to say what x, y, and z are. Well, x is 3 plus 4t, y is 1 plus 1t, and z is 5 minus 1t. That's in parametric form. Okay, in symmetric form, bring the 3 over, divide by the multiple of 4. Bring the 1 over, divide by the positive 1. Bring the 5 over, divide by the negative 1. Okay. Now, I'm going to do this all again. Do it in blue. Make it look different. Instead of using 315 for W, I'm going to use 724. I have all the space I can have. So U is still the same. 4, 1, negative 1. And W is now 724. So X will be W, 724, plus a scalar multiple of T, of U I meant to say, 4, 1, negative 1. I do have one slight error here. I ran out of room, but right here, I should say that T or even up here. Up here, I should define T. T goes between negative infinity and not equal to, nothing ever equals infinity, between negative infinity and infinity. Even over here, I should say that T goes in between negative infinity and infinity. Over here, I don't need to say what T is because there are no T's. Okay. So, what I get is 7 plus 4T, comma, 2 plus 1T, and 4 minus 1T. That's X, that's Y, and that's Z. And you may say, but wait a minute. You told me they were going to be equal. You told me that they were going to be equal. Well, here we have X is equal to 3 plus 4T, and over here we have X is 7 plus 4T. Are they equal? Well, not for the same T value. Like if T is 1, you get 3 plus 4 times 1, or 3 plus 4, which is 7. And over here, you'll get 7 plus 4 times 1, or 7 times 4, which is 11. The top one gave me 7. The bottom one gave me 11. So you say, what do you mean? That they're not equal? Well, the T's are different. This T is always one smaller than that T. For example, if T is equal to 1, the top one, T is 1 for this T here. So you get 3 plus 4 times 1. 3 plus 4 is 7. So this is 7. But the bottom T here is 1 less. 1 less than 1 is 0. 7 plus 4 times 0 is 7 plus 0, which is 7. They're equal. If I let this T be 5, 4 times 5 is 20. 3 plus 20, 23. If I let T be 5 here. Here, I let T be 1 less. I let it be 4. 4 times 4 is 16. You know what? 7 plus 16 is 23. They are giving us the same answer. So the way you write it is not unique. I guess it is safe to say there are two ways of writing it. One way was using the point P1, 315, and another way using the point 724. So there's more than one way of writing the answer, which is pretty neat. So now we go on to another type. How do you find, a plane can be determined by a point on the plane and a perpendicular and a vector perpendicular to it. Now, let us talk about y. Y is a plane determinable by one point and a vector perpendicular to the plane. Now remember, if the vector is perpendicular to the plane, you can move that vector so it crosses that point. For example, in R2, if you have this vector, happens to start at the origin. Well, if you put any point on the plane, that point, I can draw the same vector that crosses that point. In fact, I didn't even have to start on the y-axis. I could have started a little bit to the right of it. Well, then I'll go further to the right. I started here. But most importantly, it crossed that point. Okay, I can move a vector so it crosses the point that I want. Okay. Now, if you take a point on the plane, now imagine, I'm not going to draw this, but imagine, well, I'll draw it and erase it. You have a vector coming straight out of the board, straight out of your computer screen, straight out. And if it was coming straight out of your computer screen from here, or there, well then please, move it there. Okay, now, if you take any point on this board, any point, that board, shouldn't this line and that vector that was coming out of the board, shouldn't those two lines meet at a right angle? Okay, you don't have to pick a point as horizontally to the right. When you come out, you're going to have a right angle. No matter what, you're going to have a right angle. If this is a point and that vector is coming straight out of the board or straight into the board, and you pick any other point, this point, and you draw it, this is going to be a right angle. You need to convince yourself of that. It's not that hard to see it. It's going to be a right angle. Okay. Now, if you have this point on the board, and this vector is coming straight out of the board, or again, straight into the board. Now, I don't like drawing this, but suppose that point that I just drew is not on the board. It's coming a little bit out of the board. Well then, this angle will not be 90 degrees. This angle, whatever it is, it's not 90 degrees. This point is on the board. This point is off the board. And this vector is coming straight out. It won't be a right angle. It won't be a right angle. Okay, so now we have a definition for the plane. You have a point and you have a vector. So you want to define our plane. And P is on the plane. P1 is on the plane. P1 is X1, Y1, and Z1. And here, let me erase some of this, please. And there's another point on the plane. Well, we want to determine, well, I take that back. All right, the next, well, I want to say one other thing first, please. If this vector and that vector, if the dot product is 0, that means it's the right angle. The dot product is 0 if and only if they're perpendicular. They meet at a right angle. They're orthogonal. The dot product is 0 if and only if. So U dot V. We are in R3. U dot V equals 0 if and only if U and V are perpendicular. In fact, it's true for R2, but we are in R3 now. Now, I take an arbitrary point, x, y, z. And here's, well, the vector that's perpendicular to the plane is just a letter. It's called the vector n. Now, we can, and let's call this p. If we found the vector from p to p1, call that vector u. Well, when will this point be on the plane? And the answer is when the vector p, p1, when I dot it with n, gives me 0. That's the only way this point can be on the plane. Every point on the plane, this point, if it's on the plane, then this vector and this vector, the dot product will be 0. If this point right here is off the plane, well then this vector dotted with vector n will not be 0. Okay, it will not be 0. So the equation of the plane is the following. Well, first, since I drew a lot of extra stuff here, let's erase it and start fresh. So we're going to derive the equation of a plane. So anytime somebody tells you a plane is in the form of ax plus by plus cz plus d equals 0, you can smile because you can say, I understand why that is. Right. So P1 is a point on the plane. If you're taking notes, write it down. P1 is a point on the plane. And P0, or just P, is an arbitrary point in space. Now, and n is the what? N is the vector that is perpendicular to the plane. It's coming out of the plane. It's coming straight out of the board. All right. Now, the equation of the plane is the following. The equation of the plane is the following. Well, how does x, y, z get to be on the plane? Well, the answer is if the vector p1 dotted with the vector n is 0, you're on the plane. But what is p to p1? Well, it's x minus x1, comma, y minus the y value, y1, comma, z minus z1. And now I dot this with n, which is a, b, c. And I'm supposed to get 0. If I don't get 0, then this point x, y, z was not on the plane. Okay? So I multiply the first components. I'll write the a first. I get a times x minus x1 plus the second components get multiplied. B times y minus y1 plus c times z minus z1 equals 0. That's the equation of our plane where x1, y1, z1 is a point on the plane and ABC is the vector perpendicular to the plane. x1, y1, z1 is a point on the plane, and the so you have x minus that point, y minus that point, z minus that point, and the a, the b, and the c was the vector that was normal to it. and just put pluses in between. Now you may say, but wait a minute, that doesn't look like the formula you just erased. Of course it does. Remember, A, B, and C are just numbers, and x1, y1, and z1 are numbers. X, y, and z are x, y, and z. That is, we do have A times x. We do have plus B times y. We do have plus C times z, excuse me. But we also have, it's going to be minus, but whatever. We have minus AX1, which is a real number. And we have minus BY1, which is a number. And we have minus CZ1, which is a real number. But when you keep, so this is AX plus BY plus CZ. And when you keep taking away three numbers, you took away a number. You took away 7. But that's the same as adding -7, or you took away -7. That's the same as just adding 7. That is, and I'm just rewriting negative, whatever. I'm just rewriting this as D equals 0. See, yeah, it really is in that form. What do you need to take with you? The third line from the bottom, the bottom line now. That's what you need to take with you. And you need to know what A, B, and C are, and what X1, Y1, and Z1 are. Now, there's only two choices. One, X1, Y1, Z1, A, B, C. One of them is the point, and one of them is the perpendicular vector to the plane. You have A times X minus X1 plus B times, try that again, sorry. You have A times, since I wrote on it a lot, I'm writing it again, it being that line there. You have B times Y minus Y1 plus C times Z minus Z1 equals 0. The nice thing is, you can forget this equation. You can rederive it. You can derive it. Okay, what comes after the X minus, the Y minus, and the Z minus is the point. Or if you have 2 points, one of those points. And what goes in front is what's called the normal vector. The vector that is perpendicular to the plane. Okay. So now we have a way of calculating the plane. Just like before we had, many years ago, you learned ways, more than one way I bet, of finding the equation of a line. Even today, we found another way of finding the equation of a line. We use determinants. Well, now we have a nice way of finding the equation of a plane. A nice way of finding the equation of a plane. In fact, we want to find the equation of the plane that passes through the point, say 4, 2, 5, and the plane is perpendicular to the point, perpendicular, we call it N. N is equal to, say, 1, negative 2, 5. We want to find the equation of this plane. Now you can reinvent the wheel and pick an arbitrary point X, Y, Z, and go find the call this P. And define Q to be X, Y, Z, and then find the vector from P to Q. And then dot that with N and set it equal to 0, because that is the formula. Or you can just say, well, you know what? It's X minus the X value of the point, and Y minus the y value of the point. And if this were, say, -5, let's change it. It's z minus a -5. That just means z plus 5. And these numbers go in front. +1 of each bracket. -2. And the last one, the z component, goes in front of the, you got it, the z. And this equals 0. And that's the linear algebra, with the Calc 3 if you prefer. But now you have to clean it up. We have 1x minus 2y plus 5z. But we also have minus 4. But you know what? Remember, the other side is 0. So when I bring the minus 4 to the other side, it has 4. 0 plus 4 is 4. And you have to add 4. When you bring it to the other side, you take away 4. And you have to add 25. When you bring it to the other side, actually, you know what? We don't usually do that. All right. So you have to take away 4. And here you have to add 4. And here you add 25. And it equals 0. So here it is. X, a number times x, followed by a number times y, followed by a number times z. That happens to cancel out. Plus 25 is 0. Ax plus by plus cz plus a constant equals 0. Remember, this is the same as 1x plus -2y. Now, I'm not suggesting you write it this way, but it is a number times x plus a number times y plus a number times z plus a number equals 0. So here's the equation of the plane that contains the point 4, 2, -5, and every single point on this plane is perpendicular to the vector 1, -2, 5. Or maybe I shouldn't say every point. I should say every vector in the plane. This is the plane, the whiteboard. This vector, I just took a line segment. I took 2 points on the line and I connected them. I took on the plane. I drew 2 points on the plane and I connected them. When you dot that vector with n, you're gonna realize that you have a right angle because the dot product is 0. Okay? I shouldn't, if I've been saying that this vector is perpendicular to a point, I didn't mean to. If you draw any line on the board and you put your pencil right here and you come straight out, you have a right angle. You have a right angle. Even if you draw this line and you kept the pen the same way, it's a right angle. Take your pencil, put it up, put the point on a wall, on your computer screen, whatever you want. Let's do it here. And hold the pen 100% perpendicular to the plane. Now, take another pencil and lie it this way. And say, oh yeah, this pencil and the other pencil that's coming straight out of the board, it really is a right angle. And then move the pencil. Put the pencil like this. And it's still perpendicular to your pencil coming out of the board. Put your pencil like that now. It's still perpendicular to the pencil coming out of the board. Any vector in the plane is going to be perpendicular to this vector n. Now, how do you find that vector n? That's a whole nother story. I mean, if you don't have the equation of a plane, how are you going to find that vector? Going to have some number of points on the plane. You're going to have, I take it, 3 points on the plane. If you have the equation of the plane, then you can figure out this n. Which is a good segue, because what if you have these 3 points? 102, 314, and 215. Now, any 2 points lie in a plane. I mean, if you have 2 points in a plane, you can put a piece, you can put a piece of paper so that those 2 points actually touch the plane. You can put a sheet of paper such that those 2 points are on the plane. I just want to move this point up a little bit. Move it here. Now, we're going to put a stick between these 2 points. Say a pencil. Okay? And we are going to then, and on the stick, it's really big arts and crafts, we're going to put, on the stick, we are going to put some glue. We're going to put glue. Okay, so we put glue. And then we attach the paper to this glued pen. And this paper is a plane. But without moving the pencil in space, that is, don't move it from here to here, don't move it to there, keeping it exactly there. Rotate the pencil. Rotate it. Rotate the pencil. Okay, but if somebody was just looking at the pencil, they wouldn't see it moving. It's not going up, it's not going down, it's not going to the right, it's not going to the left, the angle isn't changing. Okay, well, what's going to happen is this piece of paper is going to rotate as you rotate the pencil. It's going to stay attached. In fact, maybe it would have been better if I said you make the pencils longer and you turned those ends of the pencil. The piece of paper is attached to the pencil. So the plane is rotating. Now, if you have one more point, So again, this plane, this sheet of paper, the plane, it contains those 2 points. But that didn't make it a guaranteed plane. That is, I can find infinitely many other planes, 360 degrees worth of planes that also contain point 1 and this point 2. But now, if I pick another point, say it's not on the whiteboard right now, but when you rotate that pencil, and the instant you hit that point, you stop. That's point 3. You stopped. Oh. And well, what if you didn't stop? If you rotated 360 degrees, there's only one time where it's going to contain point 3. That is, 3 points determine one plane. 3 points in space determine one plane. If somehow in the middle of your room you can take 3 marbles and just magically have them just be in 3 places in space, and you take a piece of paper, don't put the marbles too far apart, then you take a sheet of paper, and there's only one place you can hold up that piece of paper where all three marbles are on the paper, touching it. That would be the plane. There is only one place that you can hold that piece of paper. And you need to convince yourself of that. It's not that hard. It's not that hard. I mean, what you do is you have a table and you put two things on the table, and then with your right hand you hold something off the table and you try to maneuver a sheet of paper so that it actually has all three marbles or whatever three objects you're using. It actually is touching all three at the same time. And that's the plane. And if you brought the paper out a little bit, it's not touching anymore. If you move the paper in, it's not touching all three marbles. Okay, convince yourself of that. 3 points really determine our plane. Now, on a linear algebra point of view, an algebraic point of view, well, let me think about that for a moment. I'll make this statement in a moment. The fact that there's 4 variables throw me off. Okay, so we know that the equation of the plane is ax plus bx plus cx. Oh, that's not true. By cz. By cz plus d is equal to 0. So, we want this to have an infinite number of solutions. All of these 3 points are distinct, not the same. One is not a multiple of the other. Okay, they don't all 3 lie on a straight line. If you have 3 points in space or on the blackboard, if they lie on a straight line, well then you have infinite number of planes. Just again, take that pencil, make it a little bit longer, and put a piece of paper. Now, clearly, these 3 points are on the paper. Glue the paper to this stick that contains 3 points. Well, if you rotate the paper, the plane's going to rotate with the paper. When you rotate the pencil, the paper is going to rotate. But those 3 points are still going to be on the paper. So we have to rule out that case. 3, so let's update it. 3 collinear points. Collinear means they do lie in a line or they don't. It means they do. If the 3 points are not collinear, then it determines a plane. So we also know that this point is going to be on it. That is a times 1 plus b times 0 plus c times 2 plus d should be 0. The second point will be on it. A times 3 plus b times 1 plus c times 4 plus d times 1. D is always being multiplied by the number 1. And then you have the third point. A times 2 plus b times 1 plus c times 5 plus d, which is the same as d times 1, equals 0. Well, this is a system of equations in the variables a, b, c, and d. well, actually, yeah, just these you need. If you are going to solve this, that is the matrix 1, 3, 2, 0, 1, 1, 2, 4, 5. Oops. 1, 1, 1, 1, 1, 1, augmented with 0, 0, 0. If you were to solve this, then you will have solved for A, B, and C. And that's what we want to know. That's all we want to know is what is A, what is B, what is C, and what is D. So you solve this system of equations and you learn what A, B, and C are. And in our case, I've worked this out, and this bottom matrix, which I need to erase, sorry, maybe I'll write it down smaller. This bottom matrix, which was 1, 3, 2, 0, 1, 1, this column is 2, 4, 5. The last column is 1, 1, 1, augmented with the right-hand side, which was always 0. If I didn't make any silly mistakes, it reduced to 1, 0, 0, 1/3, 0, 0, 1, 0, 4/3, 0, and 0, sorry, negative 4/3, 0, 0, 1, 1/3, 0. Okay. Now, I need some space above the matrix, so let's get rid of this for now. Okay. The variables are A, B, C, and D. The first column has a non-zero, a leading entry, a non-zero entry for some row. It happened to be row 1. I don't care about that. The second column has a leading entry for, coincidentally, row 2. The third column has a leading entry, a first non-zero entry for row 3. The fourth one does not have that. That is, D can be anything. So, A, B, C, D. D can be anything. Let's call it R. Well, 1A plus nothing. That's nothing. That's 0. Plus the third D is 0. 1A plus the third D is 0. Bring this to the other side. 1A is negative a third D. But D I'm calling R. The second row, it says 0A plus 1B plus 0C, which is just 1B, minus 4/3 D is equal to 0. Well, if you bring this to the other side, you get that 1B is 4/3 D, but D is R. D is R. The third row, C, well, third row tells us that 1C minus 4/3 D is 0. Bring this over and you get that C is 4/3 D. But D is R. D is R. So this is a solution. But you know what? Nobody likes fractions. Nobody likes fractions. R can be any number. That is, I could write down a new R, which is 3 times the old one. let r equals 3 times the old r. Or you know what? How about r over 3? How about r over 3? So we know that a is negative a third r, which is really negative 1 times r over 3. So it's just negative 1 big R. I just let this r be 3. And b is 4/3 r, which is 4 times r over 3. But that's big R. So I get 4r. And c is 4/3 r. Are they both 4/3 r? Well, unfortunately, I erased things, but in my notes, that was supposed to be negative 1/3 r. So c is negative. So yeah, that's what I have. Okay, so c is negative 1 times r over 3, which is negative 1r. And d is r, which is 3r. 3 times big R gives me little r. So little r is 3r, 3 big R. And I'd rather say that a, b, and c are these numbers. Now look, all I did was take 1/3 r and triple it. Negative 1/3 r. I just replace r with 3r. I replaced 4/3 r with 4/3 times 3r. Negative a third r was negative a third 3r. I replaced r with 3r. So I got negative r by design. I get 4r by design. The 3's in the bottom keep disappearing. And this is exactly what I got over here. I cleared out the fractions. I said, oh, all of these have 3 in the bottoms. Well, the least common multiple of the denominators are 3. So I multiplied everything by 3. It's cleaner to give this set of answers. Okay. But still, that doesn't give me the equation of the plane. That still doesn't give me the equation of the plane. Okay, but it almost does. Almost does. Just pick a non-zero value for r. Pick a non-zero value for r. My advice would be to always let r be 1. Because if r is always 1, then you already have the results. That is, a is negative 1. Negative 1 times x. And remember, ax plus by plus cz plus b is 0. You already have a. B is 4 plus 4y. C is negative 1z. And d is 3 plus 3 equals 0. This is the equation of the plane. Now you may say, but wait a minute, you said you can pick any number for r. Fair enough. Let's pick 2. So negative 1 times 2 is negative 2x. And 4 times 2 is 8. So you have 8y. And negative 1 times 2 is negative 2z. And 3 times 2 is 6. Yeah. These two are the same. I know they are. Because if I divide both sides by 2, I get the line above. Because that will be negative 1, that will be 4, that will be negative 1, and that would be 3. And that, of course, is still 0. Let r be 1. Now, if you want to insist on using these numbers, well, then just let R be 3. Not numbers, but if you want to use these expressions, just let R be 3. Just let R be 3. So let me write it down like we had it at the beginning before I separated the division into products. And that will be that. Earlier, we said our final answer was A is negative R over 3, and B is 4R over 3, and C is negative R over 3, and D is R. Well, just let R be 3. So you get negative 1. You have 4 times 3 over 3. B is 4. You have negative 3 over 3. It's negative 1. 3. Okay, so you got the same answers for A, B, and C. Okay, I know I made that much more complicated, but just solve the system of equations, and you have AX plus BY plus CZ equals 0, plus D, I hope I said, and then erase most of this. You have AX plus BY plus CZ plus D equals 0. Plug those three equations, those 3 points, one by one, into their equations. That is, you're going to have 1x plus 0y plus 2z plus D equals 0. The next one will be 3x plus y plus 4z equals 0. And then 2x plus y plus 5z equals 0 plus D equals 0. And then you solve that system of equations, and you'll get A, B, C, and D. All right. Now, couple of problems we're going to do. We want to find 2 planes whose intersection is a line. Whose intersection is the line x equals 3 plus 2t, and y we'll say is 4 minus 2t, and z is going to be negative 2 plus t. We really should say that t can be any real number. This is in parametric form. I know it's parametric because they all have the t. So first you should write this in symmetric form. X minus 3 over the 2, y minus the 4 over negative 2, and z plus 2 over the understood 1. Okay, what you do at this point is you find the plane from those, you find a plane from the equation of a plane from those 2 equations, and then you find the equation of the plane from those 2 equations, and you will have found the 2 planes. That is, x minus 3 over 2 is equal to y minus 4 over negative 2. If 2 fractions are equal and they have the same denominator, then the numerators have to be equal. I'm going to multiply that top by negative 1, and I get that. I multiply the bottom by negative 1, and I get that. Well, this tells me since the 2 fractions are equal and they have the same denominators, that just tells me this. I'm going to bring everything to one side. You get x plus y minus 3 minus 4 minus 7 equals 0. That is the equation of one plane. Z can be anything. So basically, in 2 dimensions, we know it crosses at -7, and the slope is -1. So it looks like this is the line. Now imagine this line coming out of the board. Don't change the angle, just bring it out of the board. In the board, that is, this point can come out of the board and in the board. And this point out, and this one out, and this one, as well as in. That's the plane. You're going to get a plane that looks something like that. You're going to get a plane. It's that line, which I'm about to put in red, but make believe it comes out of the board and in the board. Don't change the angle. Okay, but it is a plane. Now, let's do the other half. What if we just deal with these two? You have y minus 4 over -2 is equal to z plus 2 over 1. I don't ever bother dividing by 1. This product, which is -2z minus 4, should equal 2y minus 4. Okay? They both have -4 on both sides, so they cancel out. Bring this over, you get y plus 2z equals 0. Those are the 2 planes. They intersect at this, on this line, or if you prefer, on that line. They're the same. They intersect there. Okay. Let's consider the next, and I think it's going to be the last problem of this section. So remember, you now have a way of determining the equation of a line given 2 points. All you do is you take the determinant and set it equal to 0. What determinant? xy and 1. And then the first point, xy, y1, x2, y2, the second point, and 1s. And you just set this determinant equal to 0 and solve. That should have been an x. Set that determinant equal to 0 and say, you know what, that really wasn't so bad. It really wasn't. Okay. It's amazing how determinants come out of nowhere, and they give us the area of a triangle, a parallelogram, gives us the equation of a line. They come out of nowhere. It's pretty nice. In fact, it's beautiful. All right. So now we want to find the following. Find the parametric equations of the line of intersection. Of the following 2 planes. Of the planes 3x plus 4y plus z plus 1 is 0, and say, I don't know, easy one, x minus y plus 2z plus 3 equals 0. So we want to find out which points are in common, because that's what you call the intersection. If it happens to be a line, wonderful. So I'll write down this one first. We know that 1x minus 1y plus 2z is equal to negative 3. And this one says, I just brought the constant over like I'm going to do here. We know that 3x plus 4y plus z is negative 1. And we solve this system of equations. 1, 3, negative 1, 4, and 2, 1, and this is negative 3, negative 1. And we solve this. I want to get this to be a 0. So I'll keep R3 the way it is, but I'll take away 3 times R1. This is 3, row 3, and this is 3 times R1. 3, negative 3, 6, negative 9. And I subtract. Get 0, 7, negative 5, and 8. You have to know your arithmetic. 0, 7, negative 5, and 8. I want that negative 1 to be a 0. And that's a 7. So multiply row 1 by 7. That puts a negative 7 there. If I just add the 7 to it, I'll get 0. That is, I'll add row 2. Maybe on the right side, I'll do this work. 7 times row 1 is that set of numbers. And row 2 is that set of numbers. And if I happen to add these, I happen to get this. So row 1 is 7, 0, 9, negative 13, and row 2 did not change. And one can say now that this matrix at the bottom left is in reduced row echelon form. It's in RREF form. Well, except for getting the ones for the leading entries. So I'm going to divide row 1 by 7. I'm going to divide row 2 coincidentally also by 7. And I get 1, 0, 9 over 7, negative 13 over 7, 0, 1, negative 5 over 7, and 8 over 7. Okay, I get that. Okay, I get what I get. Now, the first column, well, let me do it slightly different this time. Row 1 has its first leading entry. There it is. Row 2 has its first leading entry. Okay, now, column 1 has a leading entry for some row. Column 2 has a leading entry for some row. Column 3 does not. So the variables are x, y, and z. Remember, we were trying to solve for x, y, and z. Oops, I erased that equation. We're trying to solve for x, y, and z. So z is some arbitrary number. Z is equal to t. Z is equal to the number t. Now, that last line says that 1x plus 9 over 7z is negative 13 over 7. The second line says that y minus 5/7 z is equal to 8 over 7. There is no third line. But the third equation is z is t. So bringing this over to the other side, we have that x is negative 13 over 7 minus 9 over 7z. But z is t. The second equation tells me, bringing this over, y is equal to 8 over 7 plus 5 over 7z. But z is t. Z is t. And there is the equation of the line where the two planes intersect. Now, why don't I let t be 7? Can I remove those 7s? Yes. And remember, t is 7t over 7. And I have to remove the 7 there as well. That is, this is 7t. I can do that. I don't really want to because I still have a 7 on the bottom here. So I really don't have a good incentive for dividing by 7. In fact, I have a strong, or letting t be 7t. I have a good incentive not to do that. For the reason being, if I let t be 1, well, negative 13 over 7 plus, let it be 2. Let's make it more interesting. Plus 18 over 7, I can easily do that because they're both over 7. But if instead I just had 9t, let t be 3. What's negative 13 over 7 minus 9 times 3? The answer is, oh my, I have to get common denominators and everything. Well, I already had common denominators. They are all 7s. Every time, every x, y, or z that had a denominator, they were all 7s. Okay, so there is the equation. Let's see, these are parametric equations of the lines, of the line of intersection. If you wanted to write symmetrical equations for that line, it's not a different process. It's not a different process than before. Just solve for t. Just solve for t and let them all be equal. X plus 13 over 7. I brought that over. And now I divide by negative 9/7 equals. Bring this over. Y minus 8 over 7 divided by the multiple of t. And I already know what t equals. Now, if this is going to bother you, fine. Just realize that t is 0 plus 1t. Bring over to 0. You want to write z minus 0? Fine, wonderful. But it's still z. And then divide by 1. T is z over 1. There is the symmetric equations. Okay, you want to clean this up by multiplying over here the top and the bottom by 7. Fine. 7x plus 13 over negative 9. You can do the same over here. Coincidentally, it's 7 again. 7y minus 8 over 5 equals z. You want to say z over 1, fine. There it is. This is probably the nicest looking of the symmetric equations. That completes the section on lines and planes.